Okay, folks, here now is the second part, part two of the video for Thursday. So hopefully you're watching this and it's not quite Thursday yet. That would be my hope. In any case, we left off in part one with explaining the periodic table, the structure of the periodic table. So that's one of the gratifying things that comes out of sort of a deep dive into the hydrogen levels, the electronic levels of hydrogen, of the hydrogen atom. We sort of can make sense of the overall structure of the periodic table, and with a little bit more investigation, we can even understand why this, for instance, the 4s gets filled before the 3d. Okay, so that had to do with the effects of shielding and the penetration of the 1s shielding. In any case, that's where we're at. A couple of last thoughts on the periodic table. One is that the 4f doesn't even get tackled, doesn't even get filled until you get to n is equal to 6 down here with cesium and barium, right? So they fill up the 6s orbital, and only then do you start tackling the 4f. Okay, and there's 14 there, and then you come back here to the d orbitals in yellow. So basically the way you read that is cesium, barium, and then you come over here and you go down here to this row here, the lanthanides, as they're called. Okay, so these ones here in yellow are called transition metals, and then we come down here to the lanthanides. In any case, there's some other subtleties that happen here. If you were to look very closely at the periodic table and the electronic configuration for each element, you would notice that, for instance, copper, silver, and gold, well, they're known as noble metals, right? They're precious metals. Here, something interesting happens, namely, you might think that copper, silver, and gold are one electron away from having their d shells filled, the respective d shells filled, but that is actually not true. Nature here fills the d shells prematurely by bringing an electron from the respective s orbital. So for instance, here we have potassium and calcium filling up the 4s, and then we start with the 3d, but we fill the 3d prematurely with copper, leaving only one electron in the 4s. So the 4s is no longer fully filled. There's only one lone electron hanging out in the 4s for copper, and we can say that copper therefore is a monovalent conductor. So it has one electron, namely the lone electron, the 4s, that gives rise to conduction. So this happens also for silver and gold, that we sort of, it's energetically favorable to just steal one electron from 4s, 5s, and 6s in order to prematurely fill the d subshell. And then here with zinc, we then come back and also fill the s orbital as well, from which we took the electron earlier. And so this also happens actually, turns out that having a full d subshell is actually a good thing. It's energetically favorable, and so that's why it happens here. It also happens again that a half-filled subshell is also energetically favorable, and this happens prematurely here with chromium, for instance. Okay, so there's some sort of exceptions to the pattern, but even those exceptions have reasons that you can sort of distill. In any case, that's all we as physicists need to know for now about the periodic table. Okay, so we want to go back to helium. Okay, so there's a few things that we don't yet know about helium even. So we certainly know the ground state of helium. right? Namely, the 1s is completely filled, and the label that we attach to that is this here, 1s and then a superscript 2. The superscript just tells you how many electrons there are in that particular state, in that orbital. So there's 2 in that orbital. Okay, and so that's the ground state. Lithium, for instance, would be labeled like this. We have a filled 1s, and the 2s then has 1 electron in it in the ground state. So lithium in the ground state would be 1s sort of squared, 2s to the 1. Okay, so that would be the notation. Now, we said the 2 electrons in the 1s orbital obviously must be in the singlet spin state, right? That's the only way that we can actually allow 2 electrons to occupy that same common wave function. The spin state allows for that. The spin state itself is antisymmetric, right? We said so that is clear. But then the question is, yeah. So here is the sort of the ground state. There's a normalization factor out front, which I left off. But that's basically the idea, right? So then, what about the first excited state of helium? What do you have to do to get to an excited state? Right. So the idea is you're going to take one of those 2 electrons and promote it to a higher state. What is a higher state? Well, 2s would be a higher state, or 2p orbital. The orbitals in 2p would also be a excited state, but you only have to take one of those 2 electrons and promote it. So then the question is, what is the associated spin state? Is it a singlet or is it a triplet? Okay, so that's what we'd like to look at next. Does it even matter? Are there spins like this or are they like that? If I promote one to an excited state, an excited wave function. So the question then again is, would the spins orient themselves like this into a triplet, say, or would they remain in the singlet configuration? Okay, and so. And does it matter? Well, it turns out that, believe it or not, it does matter, okay? Because one of those 2 configurations will turn out to be energetically lower than the other. And it's not even clear why that is, but just to give you the answer up front, it's going to be the triplet state is going to be preferred. Okay, the triplet spin state is preferable slightly, okay, not a huge energetic difference, but just a slight preference. And to understand why that is, we have to look at a particular expectation value, and that will then lead us to this notion of exchange forces. Without having said what exchange forces are, I will say that they are purely a quantum mechanical phenomenon that has no equivalence in the classical world, no analog in the classical world. This is a purely quantum mechanical effect, kind of like entanglement. Okay, so we want to look at the following expectation value for different states. So here's one, an expectation value of the distance, okay, between the 2 particles, R1 minus R2 as vectors, absolute value. Okay, that is slightly easier to do if we go down 2 dimensions into 1D. Basically, we would be evaluating something like this on the x-axis. Okay, so of course we can multiply that out, and we can write it like this. And that will actually be helpful for us in a minute here. This is how we actually will evaluate this thing. But the question first is, why do we even care? Okay, why are we interested in this kind of expectation value? We have to have that that idea up front, because the calculations are going to get a little bit messy and involved and tricky, and you don't want to do all this work if the payoff is not is not good enough. There's got to be some kind of benefit for doing all this work, and so let's take a look here. Why would that expectation value be of interest to us? Okay, so the expectation value gives us the mean separation distance between the two particles relative to different states. So these two particles can be in different two-particle states. What is the two-particle state? Well, in general, it will just be something like that, psi of x1 comma x2, some two-particle state. So relative to a particular two-particle state, we can now evaluate the expectation value of the separation distance. So what's sort of the average distance between the two particles when the two particles are in this two-particle state? That's a mouthful, right? When the two particles are described by a particular two-particle wave function, then what is their mean separation? Now, again, you could ask, why would I care about that? Well, with helium, it's 2 electrons, right? And so maybe it would be kind of nice to know what the separation distance is on average between those 2 electrons, because those 2 electrons repel each other. Okay, and so there's this interaction term between those 2 electrons, that repulsive electrostatic, potential energy. I can even write it here. It's E squared over 4 pi epsilon naught times 1 over R, right? R being this x1 minus x2. And so if I know sort of on average how far these guys are from one another, then I also know what the overall contribution is of the interaction term. Okay, so that's the payoff. That's the goal that we're working towards. Okay, so having said that, now we're going to launch into a whole set of very detailed calculations. Okay, but have the bigger picture in mind as we're doing it. We're trying to estimate the repulsive interaction between electrons. Okay, so we already said we're going to do it this way, right? We're going to tackle it in 3 pieces. And we also assume that the state that we're taking these expectation values with respect to are first, we're going to just look at the distinguishable state. Okay, and sometimes the book will use the subscript D here for distinguishable. So first, we're going to try to evaluate this for 2 distinguishable particles. So we already know it's unrealistic, right? Because 2 electrons are indistinguishable fermions. So this is not going to cut it. But we're going to start here because the calculation is easier to do with this ansatz. All right, and plus there's also another reason, because in the end we want to see, okay, what does this this indistinguishability of fermions really contribute relative to, say, distinguishable classical particles? How much does it differ? Okay, so first have to figure out, well, what is the answer for this problem here? And so let's do it. All right, so how would you do it? Well, it's basically a double integral. This is how you would always evaluate any kind of expectation value. You'd basically do the integral of psi squared or psi star psi. Okay, you squeeze what you are interested in between the psi star and the psi. Okay, but in this case, we can also group the psi star and psi together and call it a psi squared, magnitude squared. Okay, and here's my x1. In this case, of course, it's going to be a double integral because this is a 2-particle wave function. Because we have to integrate over all of configuration space, over the entire space, over the entire domain of this wave function. Domain actually is a 2-dimensional domain. right? So these limits here are minus infinity to infinity, and we have to do a double integral of this sort. You with me so far? Okay, that's the basic integral we'll have to do. Okay. Now let's plug in our ansatz, and then it looks something like this. Okay, now you can see that I can separate that into two integrals, two separate integrals. Okay, because this piece here depends only on x2, this piece only on x1, and so I can separate it out, and I get something like this. Okay, so what's the next step here? Do you see it? This is now a single particle wave function. I'm integrating over a single variable. Okay, that's got to be 1, right? That's got to be 1. First term is 1 because we have a normalized single particle wave function. And so I'm really just ending up with this second integral here. Okay, now here comes another really great thing that we have to just internalize, because it's going to happen multiple times from here on. We can say that this x1 is sort of a dummy variable. It's just it's getting integrated out. All right, so it doesn't really matter what you call it because it's a variable of integration. The result will not depend on that variable of integration because we're integrating it out. It's a definite integral. So I might as well just drop the subscripts. I might as well just call x1 x. Right? There's no reason to really keep the subscript at this point. And so this is perfectly fine. Okay, and so now this here is nothing other than the expectation value of x squared relative to the single particle wave function psi sub a. So we're going to denote it like this: x squared in these brackets with a subscript a. It's the expectation value of x squared relative to a single particle wave function psi sub a. Okay. You can do the exact same thing for x2 squared, and you would get basically x squared expectation value with respect to psi sub b. So that's very easy to see, very quick to see. If you need to go back, just pause this video, go back, and you'll see why that is the case. Now, on to the third term. Okay, also not very difficult, really. We now need the expectation value of x1 times x2. Okay, and here we basically have this double integral again, same as before. In this case, now x1 and x2 appears. x1 times x2 appears as in the integrand. Okay, so again, this can be separated into two integrals. x1 goes with the first integral here, x2 goes in the second integral. Okay, and so this is also very clear what that is. Namely, it's just the expectation value of x, once I drop the subscript here, relative to the psi sub a state, and then the same here for psi sub b state. Okay, and again, the subscripts were dropped because they are dummy variables anyway, and so I can write it like this. Okay, so putting it all together, then we get that relative to the distinguishable two-particle state, that is our answer. That is our answer in short form. Okay, so we're gonna keep doing it now relative to the more realistic fermion and boson states, two-particle states. This here was done for the distinguishable case. What about identical bosons and identical fermions? And let's do the boson first, even though in the end we're really going to be more interested in the fermion case. The two really go hand in hand. The only difference will be that for the bosons there's a plus here, and for the fermions this would have to be a minus sign, right? So this is the correct two-particle state when we're talking about bosons, it has to be symmetric under exchange, and this is what it does. This kind of form guarantees that. So now, can we do all these expectation values again? Right, so relative to that state, what is that inter-electron distance on average squared? So what we have to do here first is find the probability density, from the two-particle wave function. So you have to go from wave function to probability. And the way we do that is psi star psi, right? Which is psi magnitude squared. So here, basically, you have two versions of these that you're multiplying through, that you're multiplying to one another. And so you can sort of convince yourself that this will be sort of the first thing that you'll get. The 1 over the square root of 2 will turn into a 1 over 2, 1/2. And then this term would be multiplied by a similar term just with stars, right? And that gives you then this first term. So here you get psi sub a of x1 magnitude squared, and this would give you psi sub b of x2 magnitude squared. And then this here would give you something very similar, okay? Right, so then it would be this squared times that squared, and this is my second term. But now we also have to deal with the cross terms, right? So there's two more terms that we have to consider. And so basically it's this star times that, which is my next term here. And then it's this star times that, which is my fourth term there, okay? So here are all the four terms. And that is my psi star psi for that particular two-particle state that goes along with bosons, okay? So now we are ready to evaluate the expectation values, okay? So what is x1 squared expectation value? Basically, what you would now do is you would take this, multiply by x1 squared through, and then integrate. Okay, and so these first two terms there would then give rise to these two terms. You can convince yourself fairly quickly that that's what would happen for the same reasons that we got that result previously. Okay, so again, multiply this by x1 squared and integrate. You'll see that we're going to get 1/2 times this here. This here we'll just integrate to 1 again, like before. This one here will give you the expectation value of x squared relative to a, and this one here will give you the expectation value of x squared relative to state b. But then what about these two cross terms? Okay, so we're not done yet, right? So we have these two cross terms. And so let's just write it out. All right, so here is my first cross term, and then here's my second cross term. What I've already done is I've separated them into two separate integrals each, one that runs over x1 and one that runs over x2. Okay, and so we can write it like this. So this is the contribution from the two cross terms from before. There's no magic going on here, folks. I'm just following the procedure, but you have to be pretty careful. That's all. Okay, you have to make sure that everything's accounted for. Okay, so something nice happens here. This here is going to go to 0. Okay, so you want to stop here and contemplate that point for a second. Why would that go to 0? Similarly, that term also goes to 0, that integral. And for the same reason. Okay, so if you have to, you can pause here and think about that before I give the answer. But the answer has to do with, you guessed it, the orthogonality of those two single particle states. Psi, psi b and psi a are distinct, different states, but they're eigenstates of the Hamiltonian. So they have to be, unless there's degeneracy, which we're not considering now, they have to be orthogonal. Okay, and so, and even with degeneracy, you can come up with orthogonal eigenstates. In any case, they're going to be orthogonal, and therefore that integral is by definition 0. Now that really makes it very nice, because it knocks out this entire thing, and we're really just left with the first two things. So that's nice. So similarly, the x2 squared, you're going to get the same answer, basically. Not hard to see. Okay, and so now we really just have to worry about the cross term. So far, if I add those two together, I get the expectation value of x squared with respect to a, and then plus the expectation value of x squared with respect to b. That's what I have so far, but I still have one more term left, namely that term, the expectation value of x1 times x2. So we're unfortunately not quite there yet. We have to still tackle this last remaining expectation value. So what would that look like? Okay, so now I have a product of x1 times x2. So this first integral here basically gives me that. That's from the first term. Okay, the second term will give you the same thing again. So when I say terms, well, you really have to go all the way back to the wave function, right? First term, second term. So when I convert the wave function into a probability density, right, then I get a first term, a second term, and then these two cross terms. So I'm going to tackle them one at a time, but this time the expectation value of what? Of x1 times x2, all right? And so, yeah, so here we are. Okay, the second term will give me the same thing. And so again, if I add them up, I'm going to get x expectation value of x with respect to a times the expectation value of x with respect to b. No surprise there. Okay, but now what about the two cross terms? Before, they just vanished due to orthogonality of eigenfunctions. They just vanished, which was nice. We never had to deal with them, but now they won't vanish. So the third and fourth terms are no longer going to be 0 because the x1 is in that integral and the x2 now is in the second integral. Right before, we were missing that x2 in here, and so then we could say this whole thing, this integral is 0. But now we can't, because the x2 is actually in there, and the x1 is in here. Okay, so nothing goes to 0 here, and the fourth term will give you something very, very similar. Okay, something like that. So you can work out the details here, but that's what you will find happens. And it's really not all that tricky even to see that. Okay, you just have to go back to psi star psi for the two particle boson wave function that we just flashed up earlier. Okay, so basically those are the third and fourth terms. So none of that goes to 0 now. But what you can see is they all have the same structure. They all have sort of the same structure. So here, and again, I can drop the subscript, right? The x1, for instance, here is just a dummy variable, and I can replace it by x. Same with this, right? And that's what I'll do next. These integrals all have the same form. I take the first one here, right? I can just omit the subscript everywhere, and I get that. And so I'm going to call that by a shorthand notation. Okay, it's sort of an expectation value. If a and b were the same, this would be an expectation value of x, but they're not the same. And therefore I'm labeling it subscript AB. Okay, so the notation does make some logical sense, right? If A and B were the same, I just wouldn't even need the second subscript. I could just say relative to psi sub A. So I just have the first subscript, but here it's of a mixture between A and B. And I'm going to call it this. With that shorthand notation, then I can write what I'm getting overall. So this was the contribution from the first two terms combined, and now I have these two cross terms giving me this and that. So this is very easy to see. So the first one gives me my AB, right? That was the first integral, but there was a times the second integral. Let's go back real quick. Times this integral. So this is what we now labeled expectation value of x sub AB. And what would we label this? Well, the only difference here is that the star is now associated with the B and the unstarred with A. So basically A and B are flipped, right? The fact that this is a subscript 2 is of no concern because I can drop it. So this then would have to be called expectation value of x sub BA, right? And so we get these two. And then here, these would be what? BA and here AB, right? So isn't that exactly what I have? BA and AB. So these are actually the same, aren't they? And so I can also write it as well, okay, so I could also write this as simply twice this, but we weren't really in the end interested in the expectation value of x1 times x2. We were interested in the entire thing, of which this is only one part. So let's collect all the information together into one, okay? And basically, we already know this, that's going to be that, but then here, okay, well, we get these two contributions. Right, so there's -2 times this, plus -2 times that, okay, and it gives you this. You can see where that is coming from, right? The 1/2 is not there because I'm basically adding this twice, so that 1/2 goes away, and I'm just left with that. But now I have to multiply by -2 times that. It gives me -2 times this. So it does work out. Now, there's one more step that we can take that simplifies this even more. Namely the fact that per our definition, the way we've defined this object, we can very easily see that when I swap the indices, I add a complex conjugate symbol overall. I'm conjugating overall if I swap. Right? And so then that makes, we can make use of that. That makes it easier to write the final results. Namely, we get that. Okay, so that is what we end up with for the bosons. So now let's redo everything with the minus sign. No, you can go back and just see where the minus sign, how it would sort of ripple through, okay, propagate through. And that's the only difference. The calculation is exactly identical except for keeping track of that one minus sign that would have to have been introduced right from the start with the definition of the two-particle wave function. Okay, so if we did that, we would get this result with a plus there. Okay, and so that's the important thing to notice, that initial sign switch, the only thing that it changes is that last term, the sign of that last term. And so instead of a -2 times this, you get now a +2 times this squared. That's really the only difference. And now the other thing that you'll notice is that the first 3 terms are identical to the ones that we also had for the two distinguishable particles, neither bosons nor fermions, but classical particles. Not classical, we're still using quantum mechanics, but distinguishable particles, right? So like an electron and a proton or something like that. So that's the result for the distinguishable case. And now we're either subtracting something in the case of bosons, or we're adding something in the case of fermions. And so the upshot then is that the mean particle distance, the average distance between the two particles, is smaller for bosons than it is for fermions. Fermions want to keep more of a distance between each other or from each other, whereas bosons have a tendency to get even closer together to one another, even compared to the distinguishable particle case, the independent distinguishable particle situation. So whereas bosons sort of crowd together more, fermions like to keep more of a distance from one another. So we get a sort of a hint of the Pauli exclusion principle even here. Fermions just do not like to be squeezed into one another. Okay, we call this an exchange force. The fermions will put up a little bit of a fight when you try to squeeze them into one another. There's an exchange force there that has nothing to do with charge repelling. This is not that contribution. This is just purely sort of a consequence of the anti-symmetric nature of the two particle state for fermions. Okay, so it's not an actual force. It's just called an exchange force. So what is the magnitude of the difference? Right, so it's the plus minus sort of absolute value of a squared of this new thing that we've introduced, expectation value sub AB. But let's remind ourselves, how did we actually define that, right? So what is this x sub AB? Well, it was this kind of thing, wasn't it? We didn't always want to write the integral, so we invented this shorthand notation, but that's what it is. Okay, so think about it. Here's your state psi sub A in red, and there's a state psi sub B in blue. And if they overlap a little bit, then we have a non-zero integral here. But if they don't overlap, so if this one goes to zero before, like if I separated the blue and the red from one another spatially, so that this gray area would go to zero, there's no overlap, then clearly this integral would actually go to zero as well, and we would not get a difference between bosons and fermions and independent particles. They would all sort of converge to the same answer. Okay, so the exchange force, quote unquote, that we get has to do with this overlap of wave functions. It is really strictly just that, is a consequence of the overlap of wave functions. Okay, and so let's go back to the thing that motivated this entire interlude, right? We wanted to figure out which of these scenarios is lower in energy. So can we answer that question now? Okay, can we answer this question? Which one is lower in energy? The triplet state on the right here, on the left rather, and the singlet state on the right. Now the triplet state, this is just one of the three triplet states, of course, that we're looking at, but basically triplet or singlet. So it is going to be the triplet, as we said earlier. So it's going to be the triplet spin configuration, but why? Okay, so we can say that as far as the spin state, the two-particle spin state is concerned, when we're in the triplet state, we have to have a symmetric, it is a symmetric configuration, spin configuration, right? Symmetric. They're both pointing up. So if you exchange them, you get the same thing back as far as spin is concerned. So it's clearly a symmetric spin state. And overall, the combined state has to be anti-symmetric. Therefore, the spatial part of the wave function, the spatial wave function has to be therefore anti-symmetric if the spin is symmetric. And so this here then has an anti-symmetric spatial two-particle wave function psi of R1 comma R2 that looks like this under exchange of particles. So it has to be anti-symmetric. So there's a minus sign there. You know, when I flip R1 and R2, I pick up an additional minus sign. So that is exactly now behaving like the state that we started out with fermions, right? And so here we get it follows that we get a larger interparticle distance or mean separation between the particles. It's larger because they're acting like fermions spatially, right? And so two electrons have, on average, a larger separation to one another. Greater separation, of course, means less repulsion, right? They're repelling each other less in that two-particle state than they would in a two-particle state that is, or two-particle wave function that is symmetric. In this anti-symmetric configuration, spatially, they're repelling each other less. They're avoiding each other more and repelling each other less. And so there's less of a positive contribution to the potential energy, right? The potential energy is partly given by this interaction term, E squared over 4 pi epsilon naught times 1 over R. And so the closer they get, the larger this becomes. Okay, and so clearly we see that this state has the lower overall energy. And comparing that state to the slightly higher state, we call them perihelium and orthohelium. If you compare the energy, the energies of those two configurations, you can get a sense of this contribution here, right? The electrostatic repulsion due to the electron-electron interaction. So you get a sense of the strength of that repulsion. Okay, thank you, folks.